Hello everyone, welcome to Worksheet 5D. In 5D and 5E, let's think about synthetic strategies. Here, let's think how to make a carboxylic acid starting from many different functional groups. Here is starting from alkyl halide. We are given a benzene ring, and outside of benzene ring we have three carbons. Let me number the carbons here. So then number 1, 2, 3 carbons, and we see that it is alkyl bromide. This alkyl bromide is, let's look at the alpha carbon. Alpha carbon has one alkyl group. So this is one alkyl group. So this one is primary alkyl bromide. And when this is treated with magnesium metal in ether solvent, diethyl ether solvent, now followed by addition of epoxide, and finally in strong oxidizing agent, sodium dichromate in sulfuric acid, and it will be completely oxidized into something else. So let's think about one by one. So first, this alkyl, primary alkyl bromide, and when you add magnesium in diethyl ether solvent, magnesium will be inserted between this carbon and bromine. So it will be becoming Grignard reagent alkyl magnesium bromide. And so this one is equivalent to alkyl carbanion and magnesium bromide. And next, this is, we're adding this epoxide. Epoxide is very reactive chemical species because of ring strain. So this carbanion will be attack less substituted carbon. Here the carbons are same condition, and we have ring opening process, and so it will be R, and here 1, 2, 3 position we have oxide. Here this one is 1, 2, 3 position. So 1, 2, 3 position we have oxide. So then 2 carbon extended. 2 carbon extension. And finally, in acidic workup, so we have sulfuric acid in water. It will be protonated, forming a primary alcohol. This primary alcohol in dichromate ion. It will be oxidized all the way to carboxylic acid. Uh, so this one is really becoming, we are extending 2 carbons from the initial carbon skeleton, and followed by the initially alkyl halide is now transitioned, converted into a carboxylic acid. That's the beauty of using those epoxide followed by Grignard reaction. And second one is also using Grignard reaction, but instead of epoxide, we are using carbon dioxide. This is solid carbon dioxide. We are using not gases, carbon dioxide, dry ice. Here, please remember, we are using dry ice. Here, first, let's again use, and up to here, this one is, let's say, this one is R group, and this is R and bromide, primary alkyl halide, and this one, magnesium in ether solvent. Magnesium will be inserted between the carbon and bromine, and this is, can treat this one as full carbon ion and magnesium bromide. And let's treat this one with carbon dioxide. Carbon dioxide, the carbon is now highly electron deficient. So this carbon ion will have nucleophilic attack and push up the pi bond to this oxygen, forming carboxylate ion. This carboxylate ion has one carbon extended. Here, carbon dioxide has one carbon. So if you want to extend one carbon, we can think about this Grignard reaction followed by working with dry ice and workup. Finally, workup. So here, acidic workup. Then this carboxylate ion will be fully protonated, forming the product, which is carboxylate ion. So one carbon is extended and it is forming carboxylate ion. Now let's see same reaction condition, but instead of Grignard reaction, let's think about SN1 reaction. Here, sodium cyanide is completely dissociated, forming sodium cation, which is spectate ion plus cyanide ion. Cyanide, both carbon and nitrogen has lone pair, and but has carbon as negative charge. So then carbon will be functioning as a nucleophile. So carbon will be functioning as a nucleophile. The lone pair of the carbon will attack this one and bromine will be leaving. So this is SN2 reaction. And in SN2 reaction, it will be forming here again. This one is R group. So R right there. Instead of, let me draw. This is linear. So then let me draw a linear structure like here. Okay. So one carbon is extended and in when you heat it up, heat, this one will be making into amide first, amide, and it will be once you heat it up, amide intermediate, and continue to heat it up for elongated time, then it will be making into carboxylic acid. So this one carbon extended, one carbon extension. And the characteristic of this reaction is it is SN2 reaction. And then we need to think about the characteristic of SN2 reaction. SN2 reaction is best for methyl bromide, but methyl bromide is rare, and so it is primary alkyl halide. This is best. When tertiary alkyl halide, then we cannot use SN2. And secondary alkyl halide, cyanide ion is also nucleophile, but also relatively mild, good base. So then SN2 and E2 reaction will be competing. So think about those limitations. SN2 reaction here, SN2 reaction, primary alkyl halide is best. And secondary alkyl halide, it is working but not easy. And this is much better than tertiary alkyl bromide. Tertiary alkyl bromide SN2 reaction doesn't work. Okay, now let's think about Error analysis in synthetic schemes. Each of the following synthetic schemes contains at least one flaw in its proposed method. Identify, explain what is incorrect in each case. So here we are using Grignard. This one is Grignard reagent. We are making Grignard reagent followed by sodium cyanide. But sodium cyanide we are using SN2. We just saw this is used for SN2 reaction. So Grignard reaction, SN2 reaction doesn't work well. So instead of sodium cyanide, we need to use carbon dioxide. Okay, then this is also, when you look it up, this is bromine alkyl halide, but the alpha carbon has two alkyl groups. So this one is secondary alkyl bromide. SN2 reaction works in secondary alkyl bromide, but not efficient method. So it is better to use Grignard reaction followed by reacting with this dry ice. That's better option. Here let's use magnesium in diethyl ether, and then it will be forming a Grignard reagent. So then magnesium will be inserted bromide right there, which is here. This one is a carbon ion, and we treat this one with dry ice. Then this one will be attack carbon and push up the pi bond. It will be making a carboxylic ion, and finally in acidic workup it will be protonated. Protonated making into carboxylic acid. Second, let's think about this carboxylic acid. The characteristic of carboxylic acid is that this is acidic. The proton is acidic. pK value around 4 or 5. And lithium aluminum hydride, the reagent, this one is strong nucleophile at the same time strong base. This is strong nucleophile aluminum hydride at the same time strong base. And acid-base reaction is faster than nucleophilic attack. So when you combine this mild acid with strong base, then acid-base reaction will occur, and lithium aluminum hydride will lose its power as a nucleophile. So we cannot use directly like this one. We have to first convert this one into acid halide. So let's treat this one with thionyl chloride, and let's convert this one into a acid halide. Then when you treat this one with lithium aluminum hydride, excess amount, and it will be making into here alcohol, primary alcohol. So 2 hydrogen will be added. So we can make this one into primary alcohol. And then we can think about other methods, how to get rid of this oxygen, something like that. Okay. So this is a flaw. I mean, first this one is making primary alcohol with lithium aluminum hydride, and lithium aluminum hydride followed by acidic workup. Second, lithium aluminum hydride will be working with this carboxylic acid in acid-base reaction. So then there are many flaws in second method. And third, we see an alcohol right there. Alcohol, the alpha carbon has 3 alkyl groups, 2 methyls and 1 ethyl chloride. So this one is tertiary alcohol, one side. And then here, the other side, we see chlorine, and the alpha carbon has one alkyl group, so this is primary alkyl chloride. Okay, so let's treat this one with sodium cyanide, and cyanide ion is a strong nucleophile, so we attack this one, and then chloride is leaving, so this is by SN2, it is making a substitution reaction. And when you treat this one with in strongly acidic condition in reflux temperature, not only this functional group cyanide will be turned into a carboxylic acid, but also this tertiary alcohol will be turned into, will be protonated, will be leaving, and E1 reaction will occur. So E1 reaction will occur here, and this one will be turned into a carboxylic acid. So both this one into carboxylic acid, and this is turned into a double bond. So we cannot have this product, the desired, I mean, the desired product. Here it says we want to keep the alcohol, but we only convert this one into carboxylic acid. We cannot achieve this transformation. In order to achieve this transformation, we have to protect the hydroxyl group using trimethyl silyl chloride, those things. Okay. Anyway, so let's move up to reaction mechanisms. It is very important to draw reaction mechanism. First, acidic hydrolysis. We have the cyclic amide, which is called the lactam. This is called the beta lactam. Beta lactam, very important functional group for antibiotics. And here we have acidic hydrolysis. How do you know? Because it is strongly acidic condition followed by, at the same time, high temperature is applied. And as you see here, the ring is opened. This one, ring is opened and making carboxylic acid into a secondary amine. And first, recognize that this amide is very stable carbonyl compound. So it is not usually react. That's why we have to use strongly acidic condition. We have to also heat it up. And let's really think about it. And in this case, we need to activate the carbonyl group first by protonation. And then we can do nucleophilic attack by water. In this acidic condition, we have water. Okay. And let's have step by step moving. Okay, the first step is very important. In acidic hydrolysis, we have to activate the carbonyl group first by protonation. That's important. Because here we have water. Water is only nucleophile here. This is a weak nucleophile. Weak nucleophile and stable substrate doesn't react. The reaction does not proceed. So we have to first activate this carbonyl oxygen. Let's activate it. This is equilibrium process. Only very small portion of carbonyl group will be protonated because it is stable. So let's protonate it. When it becomes protonated, then it becoming very reactive because we can draw resonance structure. Here we can draw resonance structure because oxygen is taking electron density away toward itself. So here we see it is now full carbocation characteristic, and like this way. Now it is ready, even though water is a weak nucleophile, because carbocation is so reactive, it will be offering right there, offering the lone pair to the substrate. And this is again a reversal process. So it will be making new bond here, OH, H positive, because this one is offered one of the lone pairs. And then let's use water as water, or we can do many things. We can use water as a base, or here in the molecule nitrogen is better base, so then we can use lone pair of nitrogen and then take this one away, and we can make another, we can make protonate. Here OH and again OH, and this nitrogen, let me draw it again. This nitrogen, oops, here 2H, and this nitrogen is now protonated and positive charge. So then we can come bring it down, the lone pair, use lone pair, bring it down and make it leave. So it is now loss of a leaving group. Ring dissociation reaction occurs, and now it is forming here OH and OH, and now nitrogen with methyl and hydrogen, like this way. This one is positive charge, and now we can use water or other amines, either way. Anyway, so big base is now taking, and followed by finally here it is carboxylic acid, and this amine is right there. So finally, and here, as you see here, hydronium ion is used right there. Hydronium ion is used up right there, but hydronium ion is regenerated. So this is catalyst. Hydronium ion is used as a catalyst. Initially, it is used to protonate the carbonyl oxygen, but later this is regenerated. So this is not used up. This is required for the chemical mechanism, but it is not used up. So it is used as a catalyst. Okay, so here this is nucleophilic attack. And make sure that every step is an equilibrium process. So in order to make the reaction, what is the source of this one moving toward the product side? We need to make it is a lot of water there, and then also, highly acidic condition, then it will be making the equilibrium moving toward the product side. Now let's also write the reaction prediction and mechanism writing. First, we are given 3 carbon compounds with ester. So this one is ester. It is very important to recognize the functional group. We have ester right there. And we have now primary amine. This is primary amine. Primary is mild base, mild nucleophile. We have a heat and pyridine as a base. This one is a base. Okay, now let's get started. So ester is stable carbonyl compound. Amine is a mild base, mild nucleophile. If it is oxygen nucleophile, the reaction would not occur. But because this is amine, amine is stronger in its nucleophilicity plus the heat is applied. So it is activated. Amine is activated after the lone pair to the carbonyl carbon push up this one to the oxygen, and this is only small amount of it will be offering it, making to tetrahedral intermediate. Ethyl group right there, and then two hydrogens, and positive charge, and this is ethyl group right there. Okay, let me draw it clearly again so you can see better. This one has, okay, this is tetrahedral intermediate. Okay, and then let's use the base, this pyridine. Let's use pyridine as a base. The lone pair is taking the proton away, making to neutral oxide ion. Acid-base reaction occurs. Nitrogen now. It is ethyl group. Let me draw. It is ethyl group, and it is hydrogen, and the lone pair is now coming down, and we have a leaving group. This is leaving group. And remember, in acidic condition, we do not make this ethoxide leaving. But this is a basic condition. In basic condition, we can make this leaving group leaving as it is. For an acidic condition, we have to protonate this ethoxide first and then make it leaving. But in basic condition, we are making it leaving. That's the difference. The first step is also different. In acidic condition, we have to protonate the carbonyl oxygen. But in basic condition, we are just to use the base. And then, of course, we need heat to make them more reactive. Heat is required to overcome the activation energy barrier. So this one is now leaving. Make them into here, nitrogen, ethyl group, and hydrogen right there, plus ethoxide. And ethoxide, it will be paired with pyridinium ion. It will be forming salt. Here, pyridinium ion, salt. And we have this product, amide. And what is the driving force for this reaction? Amide is more stable than the ester. So thermodynamically, amide is lower in energy. So this energy difference, delta G, is spontaneous. Delta G is negative. It is spontaneous. It will be moving toward the product side. Second, let's think about a cyclic ester. Cyclic ester called lactone. We have four-member ring structure. We have a ring strain there. That's one of the motivation for make the reaction going to the product side. We have ethyl magnesium bromide, Grignard reagent, and so this is very strong nucleophile, strong base. Okay, now let's write this ethyl magnesium bromide. This one we can write it as carbon ion and magnesium bromide for our purpose because it has strong like ionic bonding characteristic. Even though it is covalent bonding, for our purpose we can write it as a nucleophile. Then this nucleophile, let's write it here and use the lone pair, offer it to the carbonyl carbon, push up the pi bond to this oxygen, generating this one is one side reaction. This is not equilibrium because the Grignard reagent is such a strong nucleophile. It is not equilibrium process. This is one side only. And let's draw a tetrahedral intermediate. And here we have oxide. And here we have ethyl group. And this is tetrahedral intermediate. So this is nucleophilic attack. Tetrahedral intermediate. Okay, then the lone pair is coming down and the ring is collapsed. Loss of a living group. Collapse of the ring. Here is motivation. The four-member ring has ring strain, not as much as a three-member ring structure, but four-member ring is not stable. Like five or six-member ring structure is stable, but four-member ring has ring strain, so it is readily opening. So then also in this is highly basic condition. Okay, like here, remember this Grignard reagent is strong nucleophile at the same time strong base. So this is basic condition. In basic condition, we can make the oxide leaving from oxide to oxide. Okay, and so this step is equilibrium process. And here now we have oxide, and here we have ketone. Finally, an acidic workup. And this oxide will be protonated to the final product. So which is OH, alcohol, and ketone. Okay, so this one is now 1, 2, 3, 4. So let me draw 1, 2, 3, 4. One side is alcohol, so it is 1, 2, 3, 4. 4 we have ketone, and then ethyl group right there. So we have ketone on one side, the other side is oxygen, alcohol, primary alcohol, primary alcohol side. So that's the process. So please, oh, this is not final. Okay, I have mistake. I have mistake. Okay. So this is a Grignard reagent. Okay, so then let me erase this one. Grignard reagent is even more reactive with the carbonyl carbon. So here, let me erase it. Erase. All right, I figured it out. And now this Grignard reagent is an excess amount. Here, two equivalence Grignard reagent. So then again, second equivalent Grignard reagent will be attack this carbonyl carbon and push up the oxygen. Here, let me erase this one again. Push up the pi bond to this oxygen, and it is making irreversible process, making into oxide ion right there, and then two ethyl group, ethyl, ethyl, and oxide right there. And finally, when you do workup, H3O plus, here H, O, H, and again O, H, 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 it'll be protonated, protonated, and it'll be protonated. Then finally we have going to all the way to the primary alcohol and a tertiary alcohol. Here, tertiary alcohol. Let me number it 1, 2, 3, 4. So this is equal to 1, 2, 3, 4. Alcohol 1, 2, 3, 4. 4 we have alcohol, and here we have 2 ethyl group. This will be our final product. Note that this ester is going all the way to tertiary alcohol, and the other side is now primary alcohol. Twice. For lithium aluminum hydride and Grignard reagent, it will be added twice, attacking twice, making into one is for the case of Grignard reagent, it will be making a tertiary alcohol one side, the other side will become a primary alcohol. As you saw me making a mistake, please do not stop at the first product going all the way to the tertiary alcohol, because the Grignard reagent is more reactive than ketone. So here, this is ketone. And Grignard reagent is more reactive toward the ketone than ester. So it'll not staying as it is. Grignard reagent excess amount will be attacking the carbonyl carbon and move all the way to the tertiary alcohol. Now let's go into the synthetic synthesis. Now let's do retrosynthetic analysis. We have a 7 carbon compound here. 7 carbon compound. We have cyclohexane ring. We have a double bond. We have carbon-carbon double bond right there. Okay, the functional group is double bond. And here we have one more carbon. This is 8 carbon compound. 8 carbon compound. And the functional group is changed to carboxylic acid. So when you think about two things, how to elongate carbon by 1 carbon. So the extension of carbon skeleton by 1 carbon. 1 carbon. Second, how to change the functional group, this alkene, into a carboxylic acid. When you think about two things at the same time, think about systematically how to elongate the carbon by 1 carbon, and then making to carboxylic acid. Remember then, this one is achieved two things. First, two methods. Method number 1, and using Grignard reagent. Grignard reagent for alkyl halide, followed by CO2, dry ice, and workup. This is method 1. And method 2, starting from primary alkyl halide, so, and then using sodium cyanide or potassium cyanide, and here let's use strong acidic hydrolysis and heat it up. We have two methods to extend the carbon by 1 carbon, and then inducing carboxylic acid. Here, so in retrosynthetic analysis, these two things keep in mind. All right. So then this one is a new carbon-carbon bond. Now let's try both of them. Can you try both of them? Yes, I think it'll work. So first, retrosynthetic analysis. Make them. Let me move this one. The side note. Side note. Let me make this one into retrosynthetic analysis, and we can make it here. First one is making it carbon ion, and then plus CO2, or we can make it into carbocation plus nucleophile. Two different methods are all available. Okay, so let's do method 1. Let's make it into alkyl halide first. So how can you change this one into alkyl halide? This one, we need to convert this one to alkyl halide. The halogen must be on the here, and this one we need to anti-Markov-Nikov addition. Anti-Markov-Nikov addition. Then it is achieved by hydrobromic acid, this strong acid with alkyl peroxide. Alkyl peroxide must be there together, going through radical process, and making into this primary bromine. Here hydrogen added right there and bromine added to the last substituted carbon, making the terminal alkyl halide. Then there, let's treat this one with magnesium, Grignard reagent in diethyl ether solvent, and the magnesium will be inserted between carbon and bromine. Let me move this one to the side a little bit so I can make more space. Okay, so here magnesium will be inserted between carbon and bromine. This is, we can treat this one as full carbon ion because full carbon ion. The negativity difference between carbon and magnesium is great, and magnesium has positive charge, and followed by CO2, dry ice. Then the carbon ion will be attacking it, moving it to this oxygen, making carboxylate ion. Here, carboxylate ion. And then finally acidic workup. Acidic workup, positive charge, and it'll be protonated. Let's take protonation, protein, and moving to this oxygen, forming final product, which is, good job. All right, now let's try method 2. So it is starting from this product, okay, this intermediate. So this intermediate, okay, let me draw this one. Draw this one this way. Okay, bromine. This is primary alkyl bromide, which is gray substrate for SN1, SN2 reaction. So then bromine right there. Bromine. Let's use cyanide ion as a nucleophile. This one is strong nucleophile relatively. And let's take the lone pair to the primary, the alpha carbon, and then bromine is leaving as bromide ion, great leaving group. So this one is make them into cyanide ion. And here, when you treat this solid, strong acidic condition, heat is required. We need to do reflux heat for about 2 hours or 1 hour or 1.5 hours, elongated time. Then this will be converted all the way to carboxylic acid. So we have these two different methods, right? Now let's move up to this part. Now we have same substrate, but the product is not a terminal carboxylic acid. It is there, right there. So then new again we can think about the same method, method 1, method 2, and one of them will not work. Let me explain. So we can think about method 1. Method 1, same as Grignard reaction. Grignard reaction followed by CO2, dry ice, and acidic workup. And method 2, we can think about elongation 1 carbon. So it is same as, sodium cyanide or nucleophilic attack followed by this one, using this one, okay? And so here we need to make alkyl halide first. Alkyl halide for at more substitute carbon is Markov-Nicoff reaction. So then here we can simply making hydrobromic acid. Then Markov-Nicoff, this one is Markov-Nicoff addition. For carbocation intermediate, previously it was a radical process, but when you do not use alkyl peroxide, when you do not have alkyl peroxide, it will be forming carbocation intermediate for tertiary alkyl carbocation. Let me see. Let me draw. So first, this one, hydrobromic acid, and the double bond is slightly basic, weakly basic, so it will be protonating, and bromine will be leaving. It will be generating carbocation intermediate here, and hydrogen added to the terminal carbon, and we'll have tertiary carbocation. And this tertiary carbocation, bromide ion is a strong nucleophile. So the bromide ion will be attack carbocation center. It will be making more substituted alkyl halide. So this is tertiary alkyl bromide. Why? Because the alpha carbon has 3 alkyl groups. Here we have methyl, here ring structure, tertiary alkyl bromide. And then we cannot use here sodium cyanide, we cannot use it. Why not? Because cyanide ion should be attacking the alpha carbon, and bromide ion will be leaving. But tertiary alkyl bromide is now highly hindered. Alpha carbon statically hindered, statically hindered. So no SN2. SN2 reaction doesn't occur. So we cannot use method 2 for this tertiary alkyl bromide. Then the only option remaining is turning this one into a Grignard reagent. Okay, let's do method 1 only. So here this tertiary alkyl halide, let's treat this one with magnesium metal in diethyl ether solvent. Then magnesium will be inserted right there. Magnesium will be inserted right there, magnesium bromide. And let's treat this one with, and first let's write this one. This is equivalent to a carbon ion. So this carbon ion and magnesium bromide. So then when you treat this one with carbon dioxide gas, I mean not gas, carbon dioxide, the dries, and it will be attacking the carbon and push up the pi bond to this oxygen, and it will make methyl right there. It will make carboxylate ion. And here, when it acidic workup, and acidic workup, it will be protonated, forming final product. Okay, so we have two different methods. We can use Grignard reaction and followed by drying ice, using dry ice and acidic workup to elongate carbon skeleton by one carbon and then inducing carboxylic acid functional group. Or we can use sodium cyanide or potassium cyanide followed by acidic condition and heating up reflux temperature for 1 hour, 2 hours. We can change the nitrile group into carboxylic acid, but that has a limitation because nucleophilic attack is preceding the acidic step. So then nucleophilic attack, it is very favorable for primary alkyl halide, but tertiary alkyl halide, nucleophilic SN2 reaction cannot occur. So in this step, we have to use Grignard reaction only. Okay, now let's do a synthesis challenge. Propose an efficient and logical synthetic route starting from the simple starting material. So here we have benzene. Starting material is simple benzene, 6-carbon compound. And we have now these groups added. So then we have, this is the new carbon-carbon bond. So we need to induce this new carbon-carbon bond, plus we have a new functional group. Here, carboxylic acid. So we need to think about these two things. We need to first making new carbon-carbon bond between benzene and this alpha carbon. Here, this alpha carbon. And then how can we make this carboxylic acid? And let's do retrosynthetic analysis. First, let's cleave this carboxylic acid. Then we can think of, because this one is tertiary alpha carbon is tertiary position, we can use Grignard reaction. So here we can make this one into methyl, here methyl, and bromine. So we can use here carbon dioxide, dry ice, followed by acidic workup. Then we can make carboxylic acid. And then now let's think about it. How can we convert this benzene ring? How can we convert this one to this compound? Can we have this compound? Okay, so we have learned about Friedel-Crafts alkylation. So let's think about Friedel-Crafts alkylation. So first, let's treat this one into with the, you know, okay. So we have this methyl, and bromine plus aluminum bromide catalyst. Then it'll be turning this benzene into, will be elongating the carbon by two carbons, methyl and methyl. And how can I make them into bromine? So this one is benzylic carbon. Benzylic position, we can do bromine by using N-bromosuccinimide. N-bromosuccinimide with the light, UV light or heat. N-bromosuccinimide is this structure. No, this one is carbon and N-bromosuccinimide. Correct. Okay. So here, this is N-bromosuccinimide structure, and the bromine, nitrogen bromine structure will be using radical process. It will be in heat. It will be going through radical process, and it will be bromine will be brominated on this alpha, the benzylic carbon right there, benzylic carbon. Okay, then it will be we are treating this one with dry ice followed by acidic workup. Then it will be making carboxylic acid. Okay, now let's move up to the B. Here we have ketone. So six-membered carbon, six-membered ring structure, and it is ketone. And we are changing this one into more elongated one. So then let's find a new, here, this one is new carbon-carbon bond. Again, here we have new carbon-carbon bond. Okay, and then let's make retrosynthetic analysis. So we need to have this carboxylic acid later. Okay, so when you go back, you can make phenyl plus, you can make this one phenyl to some kind of functional group, making into carboxylic acid. Then we can think about again the Grignard reagent plus dry ice condition or sodium cyanide. But here this condition again, tertiary condition. This is tertiary. So we cannot use the sodium cyanide method. We have to use CO2 followed by acidic workup. So then this one must be Grignard reagent. Then this one must be Grignard reagent. All right. Then how can you make this Grignard reagent? Also adding this phenyl ring, and when you add phenyl ring right there, the new carbon-carbon bond can be, we can think about Grignard reaction, or we can think about, we have learned the Gilman reaction, alkyl thialkyl cuprate. All right, okay. Then let's try Grignard reaction, because that's very, Gilman reaction doesn't work. This one not working with ketone. Grignard reagent is working with alkyl chloride. So this is out of our consideration. Now let's try Grignard reaction. Okay, let's first then use Grignard reagent. Then phenyl magnesium bromide, phenyl magnesium bromide, followed by acidic workup. Then this phenyl group, carbon ion, will attack the carbonyl carbon and then push up, and later it will be protonated, forming a tertiary alcohol. So we have here phenyl ring and then tertiary alcohol. So this is becoming tertiary alcohol. How can we turn this tertiary alcohol into Grignard reagent? First, let's use acidic condition. So tertiary alcohol, let's use acidic condition and then bromide. So let's use strong acid, hydrobromic acid. Then by E1 process, not E1, SN1 process. SN1 will be making into alkyl bromide. Let me draw the structure, draw the mechanism of this one, this tertiary alcohol. This alcohol is, hydroxyl group has a lone pair. This is a weak base. So hydrobromic acid, right there, this is strong acid. Strong acid. It'll be protonated. It'll be protonated first, making into good living group. This is good living group. And because it's tertiary, we cannot attack this one slowly. By this one should be leaving by itself, slowly leaving. Rate determining step, slowly this is leaving, generating a carbocation center, and then bromide ion. This one is strong nucleophile, so it will be attack the carbocation center, forming our tertiary alkyl bromide. And then you treat this one with magnesium in diethyl ether solvent. They will be making this tertiary alkyl magnesium bromide, and they will be treated with carbon dioxide and acid workup. It will be making into final product. Okay, so all right, that's it. Today's work. Let me see. Okay, that is it in today's work. So today we saw synthetic strategies in combination with many of the methods we have learned in in organic chemistry 1. Also, we have learned in OChem 2. We we are putting the pieces together, making into a big picture. And I recommend you to take a blank paper always and then try it a couple of times more to gain more experiences. How to make these multi-step reactions, how to do retrosynthetic analysis. And here we saw really one key student learning objective for this worksheet is how to make elongation of the carbon backbone by one carbon and then inducing the carboxylic acid. We have two different methods. First, Grignard reagent, preparation of Grignard reagent, alkyl magnesium bromide, followed by dry ice, reaction with dry ice and acidic workup. Second method is using cyanide ion, sodium cyanide or potassium cyanide, and followed by in acidic condition, heating up for 1 hour, 2 hours. Then it is turning into a carboxylic acid, elongating the carbon chain by one carbon, but there are limitations. For sodium cyanide, we have to use primary alkyl bromide as a substrate. If it is tertiary alkyl bromide, we cannot use sodium cyanide because SN2 reaction does not occur for a tertiary alkyl bromide. And then we were able to think about many different mechanisms. Highly recommend you to draw the mechanism. So acidic hydrolysis of ester, basic hydrolysis of ester, and also same thing for amide. And then reaction with Grignard reagent or lithium aluminum hydride. Those things, try to draw the mechanism and gaining understanding. Thank you everyone for watching this one. I will see you in next video.